Friends, welcome to VK Lectures. In this lecture, we are discussing the quantum mechanics part, which is the perturbation theory. So, perturbation theory, it is a technique used to understand and solve complex quantum mechanical systems. Now, what is this complex quantum mechanical system and how is it different from simple ones? Now, for the complex quantum systems, there is apart from the simple electron or a proton or any particle, there are the interaction between two particles is considered, or some external force is being applied. These are to be considered. Now, what is a simple quantum mechanical system? For example, let us take the hydrogen atom. Hydrogen atom is in general is considered as a simple quantum mechanical system where an electron, here you see the electron is orbiting around a nucleus which consists of only proton. Okay. So this is a simple quantum mechanical system. Now, to describe this, we have the wave function for the hydrogen atom, which is given by 1 by pi a naught cube under root e to the power minus r divided by a naught, where a naught is the Bohr radius. Okay, this is a simple quantum mechanical system where we define the wave function of this hydrogen atom by this simple equation. Now, in reality, this quantum mechanical system that we have taken, that is the hydrogen atom, is not as simple, because it not only consists of an electron but it also consists of a proton, and this electron and proton are being interacted because of many forces. One, for example, is the electrostatic force, F electrostatic, and since they have mass, there is another interaction due to mass of the object, which is Fg, which is the gravitational force between them. So there are many more aspects to the simple hydrogen atom, so it becomes more complex. So in order to solve such complex systems, we introduce the perturbation theory, which accounts for the electron proton interaction as well. Now let us see how can we apply the perturbation theorem. Now consider, we have the first thing that we have with us is the unperturbed system. That means the original system, just like hydrogen atom in general that we have discussed, without the interaction, without considering, this is important here, without considering the electron and the proton interaction. So this is our unperturbed system, and we know how to solve this. We take the energy, the potential of the particle, and get the wave function psi, which is equal to 1 divided by under root pi a naught cube e to the power minus r divided by a naught. So this is how we get, and we solve for different quantities, like position, momentum, the expectation values, etc. So, but what happens when perturbation is added? Okay, the next thing is the addition of the perturbation. Perturbation is the electron proton interaction. So this interaction is being added to the first one, making it perturbed wave function, or this interaction is considered as the disturbances to the unperturbed system. Okay, Now we look into the next aspect, that is the first order correction. The first order correction to energy levels and wave function of the electron is calculated by taking into account the effect of perturbation. So how much is the perturbation? Based on that, we would uh, consider the correction. For example, the pi value, we know that pi is equal to 3.14. We need the corrections now. What is the digits? All these digits afterwards is the correction. Every digit that we add is the correction. If you call it as the first order correction as the first term, so let it be, this is 1, this is 2, or this is 8. So all these points corresponds to first order correction, second order, third order, fourth order. Okay, so if this is the unperturbed state energy or wave function or any particular quantity, the next term that is being added to this is considered as the first order correction, second order correction. That is called the order of the correction. It is represented by lambda power 0, lambda power 1, lambda power 2, lambda power 3, etc. So this represents the unperturbed one. This is first order, second order, third order, and it goes on. Okay. Before going to the physical insight, let us also understand with the one more kind of analogy that we can make. For example, cos theta, we can write it as 1 minus theta square by 2 factorial plus theta power 4 by 4 factorial minus theta power 6 by 6 factorial, etc. Now for me, I can consider cos theta equal to 1 minus theta square by 2 factorial. Let this be the first order. So this becomes the first order correction. I have added to the value, I have added something or subtracted something, 1 minus theta square by 2. So this becomes my first order correction. And if I add theta power 4 by 4 factorial, it becomes the second order correction. And if again I add minus theta power 6 by 6 factorial, it becomes the third order correction. So this is the first order correction, this is the second order correction, and this is the third order correction, and it goes on. So this is first, second, and third, and it goes on. So this is how the correction is being done. Based on the order of the correction, we get the more accuracy in the reading. Now another aspect is finding the insight of or the physical meaning. Now for example, when I consider the hydrogen atom, I can say this is the ground state with 13.6 electron volt, and here you have 13.6 by 4 electron volt, and over here we have 13.6 by 9 electron volt, and so on. Now small addition of the perturbation, it may give to rise to some other value. It might be 13.6 2 electron volt. Let's just for an example, this is 13.62 electron volt. Now again corresponding to that, there will be a small change occurring here as well as here. Earlier we had a different spectrum of energy levels, all hydrogen atom energy levels, or we can say different spectrum, Lyman, Balmer series, etc. We have different series for the hydrogen atom. So when we add perturbation, this series also get affected. So this is how it differs. First thing is the first order correction helps to understand how electrons energy levels and wave function are being affected. So for example, energy E naught changes to E dash. Similarly, the wave function psi naught changes to psi dash. And this also give rise to change in the atom's spectrum. So atomic spectrum also changes. Now this is a more prominent in looking into when we look into the spectrum, the atomic structure. In atomic physics, we deal with considering electron, the nucleus is over here, and electron. We used to make all calculation based on the fact that the nucleus is more heavy than the electron, and we neglect the mass of the electron, neglect the mass of electron, and then we calculate it. But we also understood that the mass of the electron has to be taken into consideration, though we have reduced mass, which gives us the mass of the nucleus into mass of the electron divided by mass of nucleus plus the mass of electron. So this is how we come down making more corrections. So that is called perturbation. One question that comes to our mind while doing perturbation is, why do we have a different order of perturbation? We have already answered, but again, just for reaffirming our ideas, we use different orders of perturbation theory to achieve increasing levels of accuracy. So as we increase the order of perturbation, we increase the accuracy in our calculations. More perturbation, order of perturbation, more closer we are to the exact value. And now each order of perturbation corresponds to including more terms. The more terms in the perturbation or the series expansion provides more detailed and refined approximation to the true solution or the true value. So this is the ultimate answer, that is, higher the order, more corrections we take into account. The more corrections that we have, more refined or more detailed our result will be, calculated result, and the exact solution or the exact value will be more clear and more precise, more accurate. Let us consider a one-dimensional box. So this is the one-dimensional box that we have from 0 to L, and the wave function as psi naught given by, it represents the unperturbed wave function, okay, or we can also write psi n of naught. So this is the unperturbed wave function representation. We can write it as under root 2 by L sine n pi x by L. Okay, sine n naught equal to under root 2 by L sine n pi x by L. And corresponding to that, we have En naught, which represent the unperturbed energy. It's given by n square pi square h cross square by 2m L square, where L is the length of the box. So this satisfies the equation H psi, where H is the Hamiltonian, equal to E psi. And what does it gives us? It gives us H unperturbed Hamiltonian acting on unperturbed wave function gives you unperturbed energy times the unperturbed wave function. If you want, you can write H n psi n n. This n represent the state, ground state, first excited state, depending on what. So n starts from 1, 2, etc. to n, whatever. Okay. Now I'm assuming that there is a perturbation or the 1D box which looks something like this. So now look at this part. Okay, this is a same 1D box, but it is slightly tilted with y is equal to mx. So this is y, this is starts from 0, this is L, this is y equal to mx, there is a y, it is increasing with slope m, and this particular voltage, sorry, particular potential is V naught. Okay, now this perturbation can be represented by the unperturbed state is here, plus there is a small state over here which is this. Okay, so this is the unperturbed state. Let us represent it by H, and this is H dash. This is H naught. Let us represent H naught, and this is H dash. So our new Hamiltonian H will be equal to H naught plus H dash, or you can also represent it by H1, indicating the first order or something. Now if this is V naught and this length is L, M can be written as M is equal to M is the slope, that is Y by X. So Y is V naught and X is L. So what is H dash? H dash is equal to V naught by L into X. So our new Hamiltonian H is equal to H naught, the unperturbed Hamiltonian, plus the perturbed one, that is V naught X by L. Similarly, if we have a Hamiltonian or the 1D box, something like this, at this point you have the infinite potential, and over it is not having the shape of the straight line, but it is a circle, semicircle. So H dash, the unperturbed Hamiltonian, will be this will be like this plus this, right? So this is H naught, and what about this? This is H dash. So H dash is having a value which is equal to some B times X square divided by L square, something, some random value, B by L square. So our new Hamiltonian H will be equal to H naught plus H dash. This gives us H naught plus Bx square by L square. So H naught is the unperturbed one, unperturbed, while this is the perturbation. Okay, perturbed state, perturbation, or you write it as perturbation. And this H is the perturbed Hamiltonian, perturbed Hamiltonian, which represent the total Hamiltonian of the system. Here in this lecture we are going to discuss perturbation theory. Now, what is perturbation? Suppose we have a state, something like this. This state is unperturbed. Perturbed means, unperturbed means not disturbed. Not disturbed state, undisturbed state. Okay, there is no disturbance has occurred in this state, so this is called unperturbed state. And this state will have a wave function psi. Let us represent the unperturbed, that means it is not perturbed, the perturbation is 0 here. Okay, so psi naught represent unperturbed wave function psi naught, and corresponding to that we have the Hamiltonian, which represent the energy H naught as the unperturbed energy. Okay, now due to some intervention, this state is being perturbed. So for example, earlier this was a rectangle, now it is some way it is deformed. Okay, so this is deformation is called perturbation, or the disturbance caused by some external agency. This external agency has the perturbation H dash. So this perturbation is being induced into this unperturbed state, and we are getting a perturbation and perturbed state. Perturbed state means the disturbed state. So the perturbed state has the wave function psi dash and a corresponding Hamiltonian H dash. Or we will generally represent it as H and the wave function psi, because let us represent the perturbation as H dash. So we can write the perturbation or perturbed state H is equal to unperturbed state or the unperturbed energy plus the perturbation. This is the Hamiltonian, what is right now present. The Hamiltonian is this was the earlier Hamiltonian, and this is the induced Hamiltonian. Okay, now we can represent the perturbation H dash as, let me write this as H dash, that is the perturbation H dash as lambda times, this is the order of the perturbation H1. So we will represent as the first order perturbation. Lambda represent the order of the perturbation, and in the bracket we have written 1, that represent the order of the perturbation, plus lambda square H2. So this is the second order perturbation, and now we have the third order perturbation. Now it goes on, it extends, because this perturbation is doesn't end here, because due to this h dash, this has changed in this form. Again, due to this a change in the formation here, or the form has changed, there is another perturbation occurring due to its effect. So effect keep on increasing, right? So now we can write the total Hamiltonian H, that is what we have written earlier. H is equal to the H naught, the initial Hamiltonian, plus what is given as H dash. What is H dash? H dash we are writing in terms of different order perturbation. So H naught plus lambda times H1, that is the first order perturbation, plus lambda square H2 plus lambda cube H3 plus etc. Now this is the total perturbation in Hamiltonian. Hamiltonian is something that gives the energy of the state. So this is the total perturbation in Hamiltonian. Now let us see what is the total perturbation that is occurring in the wave function. So let us write the total perturbation in wave function. So definitely when there is a change in energy of a certain state, it will its wave function also will change. So total perturbation in wave function is equal to, let us write the total perturbed wave function as psi, equal to, that is the initial, which is unperturbed wave function, plus lambda times first order correction to the wave function, plus lambda square psi 2 plus lambda cube psi 3 etc. So what about this energy? So total perturbation in energy, how we can write as E is equal to E naught plus lambda times first order correction to the energy, plus lambda square times second order correction, plus lambda cube times the third order correction, and it goes. So here is the total perturbation in Hamiltonian, the first equation. The second equation states the total perturbation in the wave function, and this third one, energy, that is the total perturbation in the energy. Now let us write down the perturbed wave function psi equal to psi naught plus lambda times psi 1 plus lambda square times psi 2 etc. Now the energy is equal to E naught, this is the perturbed energy, E naught plus lambda times E naught E1 plus lambda square E2 etc. Corresponding to the wave function, the Hamiltonian is H is equal to H naught plus lambda times H1 plus lambda square times H2. These all are the order of the perturbation. Now we know h psi equal to E times psi, where E is the eigenvalue. Now let us focus on the left hand side. Let us write down what is h. H is equal to h naught plus lambda h1 plus lambda square h2 etc. times psi. What is psi? Psi is psi naught plus lambda psi 1 plus lambda square psi 2 etc. Now h naught will go with psi naught plus h naught into lambda psi 1 plus h naught into lambda square psi 2 lambda square psi 2. Now plus lambda h dash, sorry, h1. So we have multiplied with h naught with all the terms. Now we will go with the second term in here. So lambda h dash will go with psi naught. Okay, fine. Now lambda h dash will go with lambda psi 1 plus lambda h dash will go with lambda square psi 2 plus lambda square h2 will go with psi naught plus lambda square h2 will go with lambda psi 1 plus lambda square h2 will go with lambda square psi 2. So it goes on. Now here the unperturbed state should go with, can only have commutation with the corresponding to that particular order. So we can write lambda naught h naught psi naught plus lambda 1. So whenever we have lambda 1, you can use this one, naught and psi 1. So it is h naught psi 1. Okay, then wherever we have lambda, just take it out. So plus lambda into h1 psi naught plus, here we have lambda square h naught psi 2 plus, here we have lambda square, we can write h1 psi 1 plus, here we have lambda square h2 psi naught plus, here we have lambda square, but look at the power here, this is 2 and this is 1, so this is lambda cube h2 psi 1 plus, this is lambda power 4 h2 psi 2. Okay, now this goes on. Now we will write in short form, that is h naught psi naught plus lambda power 1 into h naught psi 1 plus psi naught or h1 psi naught. Okay, these two values. Okay, this is also included. Now plus, now we have lambda square. Either it has to be h naught psi 2 plus h1 psi 1 plus h2 psi naught. Now I hope you understood how to write the terms. This is h naught, the sum of the superscript has to be equal to the power of the lambda. So it is lambda power 1. So this is 0 plus 1. This is 1 plus 0. This is lambda square. So 0, 2, 1, 1, 2, 0. So suppose if you have lambda cube, so how we can write that? It will be starting from h naught psi 3 plus h1 psi 2 plus h2 psi 1 plus h3 psi naught. So this is how our terms. So this is the first order correction, this is the second order correction, sorry, this is the zeroth order correction, that is the unperturbed energy, and this is the first order correction. Here is the second order, this is the third order. See, this superscript will tell you the order of the perturbation. So similarly we can write it for, we have just written for h psi is equal to E psi. Now we can similarly write it for the right hand side, which will be as follows: lambda naught times E naught into psi naught plus lambda 1 E1 psi naught plus E naught psi 1 plus lambda square, the second order correction, E2 psi naught plus E1 psi 1 plus E naught psi 2. Now for the clarification, lambda cube, the third order, E3 psi naught plus E2 psi 1 plus E1 psi 2 plus E naught psi 3. So this is how we can write the perturbation in energy. For lambda power 0, we can say it is the zeroth order perturbation. Zeroth order perturbation. Zeroth order perturbation is simply means unperturbed state or unperturbed value. Now this is given by from the first one, that is E naught psi naught equal to h naught psi naught. Now for lambda power 1, this implies the first order perturbation. First order perturbation. h1 psi naught plus h naught psi 1 equal to e1 psi naught plus e naught psi 1. Now similarly for lambda square gives the second order perturbation. We can write h naught psi 2 plus h1 psi 1 plus h2 psi naught equal to e naught psi 2 plus e1 psi 1 plus e2 psi naught. So this is the second order perturbation. Now let us see the first order perturbation, that is the correction to the energy. First order correction to energy. This is given by En1. So this 1 represents the order of the correction. Then En represents the state, at what is the state of the system. Now this is given by psi n naught h dash psi n naught. Now psi n naught, both are the initial states, and h dash is the perturbed energy, Hamiltonian. This is also given by simply the expectation value of h dash, or if I can represent this n with the state h dash n. Now in integral form we can write this in this particular form: integral psi n star h dash psi n dx. If it is one dimension, it is dx. If it is two dimension, dA. Three dimension, dτ. So this is how you can find out the first order correction to energy. You can either use this or the integral method. Now here let us see few of the commonly used or commonly available perturbed Hamiltonian in our different systems. For a charged particle, in electric field E, you can write the perturbed Hamiltonian H dash is equal to Q E X, where X is the position operator, E is the electric field, and Q is the charge. Now for normal Zeeman effect, the H dash is equal to minus mu L into B bar dot B bar. So that's equal to GL E divided by 2m B into LZ. GL is a constant corresponding to the orbital angular momentum. E is the charge, electric charge. M is the mass. B is the magnetic field. LZ, the angular momentum corresponding to Z, axis. Now, for anomalous Zeeman effect, H dash is equal to Gj E divided by 2m B into Lz. Now Gj as the constant corresponding to total angular momentum, where J equal to L plus S, which is orbital angular momentum and spin angular momentum, and B is the magnetic field.